Okay. Section 13.2, derivatives and integrals of vector functions. So the derivative of a vector function is just, well, the defined the same way we define a derivative of a regular function. Basically, we will just take the derivative of each of the components, uh, of each of its components of that vector function. And so the derivative of r with respect to t is just a limit as h goes to 0 of the vector function r evaluated at t plus h minus the vector function r evaluated at t, all divided by h. A better way of stating this, it's a limit as h goes to 0. There exists some function r prime of t such that the vector function r prime of t times h, this is some linear function satisfying the following. The limit as h approaches 0 of r at t plus h minus r of t minus r prime of t times h, all divided by h, that is equal to the 0 vector. The tangent vector to the curve is defined by the slope of the tangent line of this tangent vector of the curve is defined as this. So the unit tangent vector, denoted by t, capital T, is just r prime divided by the norm of r. So we have the following theorem, that if r is the vector with components f, g, h, so f times I plus g times j plus h times k, where f, g, and h are differentiable functions, then the tangent vector to r prime, is equal to the vector f prime, g prime, h prime. You can write it as according to the standard basis, f prime I plus g prime j plus h prime k. So let me give you the standard sort of properties of the derivative. So the derivative of this vector function satisfies all the standard sort of properties that you think a derivative should have. So theorem. Suppose u and v, the vector functions u and v are differentiable vector functions. Suppose c is some real number, f is some real valued function. Then the derivative of the vector functions u plus v is just equal to the derivative of u plus the derivative of v. Second property, the derivative of c times the vector function u is just c times the derivative of the vector function u. The derivative of the product of the function f times the vector function u is just the derivative of the function f times the vector function u plus f times the derivative of the vector function u. Property 4. More or less Leibniz rule. The derivative of the vector function u dot the vector function v is equal to the derivative of the vector function u dot the vector function v plus the vector function u dot the derivative of the vector function v. And, well, again, a Leibniz type of rule. The derivative of the vector function u cross the vector function v is just the derivative of the vector function u cross the vector function v plus the vector function u cross the derivative of the vector function v. Property 6. Oh, that's the last of those properties. We have basically the chain rule. The derivative of the vector function u evaluated at the function f is just the derivative of the function f times the derivative of the vector function u evaluated at f. Similarly, you can define the integral. So suppose you have some vector function r with components f, g, and h. Then the integral from a to b of the vector function r is just the vector function with components, the integral from a to b f, comma, the integral from a to b g, comma, the integral from a to b of h. And so the way you take the integral is you just take the integral of the components. On page 900, let's do problem, let's do problem 8 on page 900. In exercises 3 through 8a, sketch the plane curve with the given vector equation. B, find the derivative of the vector function r. C, sketch the position vector r and the tangent vector r prime for the given value of t. Okay, so I have here that r is equal to cosine t plus 1 times I plus sine t minus 1 times j. And t here is equal to negative pi over 3. And so this looks like a circle of radius 1, centered at 1, negative 1. Okay, let me do B. So for part B, I want to find the derivative. So let's find the derivative. The derivative of cosine is minus sine. The derivative of 1 is 0. The derivative of sine is cosine. Derivative of negative 1 is 0. So that is the derivative. C. I want to sketch the position vector r and the tangent vector r prime. Okay, so, and I want to do this when t is equal to negative pi over 3. So at t equaling negative pi over 3, I have that r, the position vector, is equal to cosine negative pi over 3. Do this a little bit better. Plus 1 sine negative pi over 3 minus 1. So this is equal to, well, 1/2 plus 1 and negative rad 3 over 2 minus 1. And so this is 3/2 negative rad 3 over 2 minus 1. I guess I'll just leave it like that. Okay, so now let's take the derivative and evaluate at negative pi over 3. And so I got here, it was negative sine. So negative sine of minus pi over 3 and cosine of negative pi over 3. And so, well, sine negative pi over 3 is a negative rad 3 over 2. So the negatives cancel, so you get rad 3 over 2. And cosine of minus pi over 3 is 1/2. So, sketching the position vector and the tangent vector, we get the following. In exercises 17 through 20, find the unit tangent vector, t, at the point with the given value of the parameter t. And so, r is equal to sine squared times I plus cosine squared times j plus tangent squared times k, where t is equal to pi over 4. Okay? And so, let's take the derivative. The derivative of sine squared is 2 sine t times the derivative of what's inside, cosine t. The derivative of cosine squared is 2 cosine t times the derivative of cosine t, which is a minus sine t. Lastly, the derivative of tangent squared is 2 tangent t times the derivative of tangent, which is secant squared t. Okay. So let's try to evaluate that when t is pi over 4. So at pi over 4, we have the following. So plugging in pi over 4, we have 2 sine pi over 4 cosine pi over 4. Of course, we're going to simplify this to sine of 2t. And so that would have given me a 1 minus 2 cosine pi over 4 sine pi over 4. And of course, I could have simplified this to, again, a minus sine of 2t, so this would give me a minus 1. And 2 tangent pi over 4 secant squared pi over 4. So this is equal to, make this a little nicer. Well, maybe I'll just, so sine of pi over 4, 1 over rad 2, cosine 1 over rad 2, cosine 1 over rad 2, sine 1 over rad 2, tangent 1, 1 second. Let me get this back. Okay, tangent is 1. Will you stop? Let me get control back. of my screen. So tangent of pi over 4 is 1, and secant is rad 2. So I get 1, 1, 4. Okay. Ooh, there's a minus. I didn't see the minus there. 1 minus 1, 4. Okay. And so let's find the unit tangent. Let me find the norm. Actually, let's find the norm squared. So this will be 1 squared, negative 1 squared, 4 squared. So 16, 17, 18. And so notational problem there. I forgot the prime, and because I forgot the prime there. Okay, so I forgot the primes that somehow disappeared. So this is the square root of 18, which is 3 rad 2. Okay, so the unit tangent vector is equal to, well, the tangent vector divided by the norm of the tangent vector. And so let's just do it on the outside. 1 over 3 rad 2 times 1 minus 1, 4. And that is your unit tangent vector. Let me do problem number 22. If r, the vector function r, has components e to the 2t, e to the minus 2t, te to the 2t, find the unit tangent vector at 0, the second derivative of the position vector at 0, and the dot product of r prime and r double prime. Okay, so let's do that. So let's find the derivative for each of these. 2e to the 2t minus 2e to the minus 2t. And you have to do the product rule. Derivative of the first times the second times the derivative. First times the second plus the first times the derivative of the second. So let me multiply by 2. Let's take the second derivative. So this is going to equal, bring down, so take the derivative, will be a 4e to the 2t. It'll be a 4e to the minus 2t. It will be 2e to the 2t. That's the derivative of the first one. Plus, I'll use the product rule for this. So the derivative of the first is going to be a 2e to the 2t. So that makes that a 4. Plus the derivative plus the first times the derivative of the second. So that's e to the 2t times 2. 2 times 2 is 4. Now let's evaluate at 0. So if I plug in 0, this will simplify this. And so e to the 0 is 1. 1 plus 2 is 3. Yeah. Let's do the norm squared, 2 squared plus 2 squared plus 3 squared. 9 plus 4 plus 4, 17. Okay. Oh, I wonder if that was a minus. I bet you this is a minus here. Okay. 1 second. I bet you that's a minus. If I do that, let me modify this. I'm hoping that's a minus there, because then that will be 2. That would be the correct. And derivative of the second will give me a minus. Okay. And then let's just check the second derivative. Those will be the same. So this will be this. Ooh, this will only be a 2 here. Then this will change. The second derivative will change, because it'll be more complicated. Okay, so it'll be a 2 e to the 2t minus 2 e to the minus 2t. Then that will be a minus and minus will be a plus 4t e to the minus 2t. Okay, so this will change. Plugging in 0, 2, negative 2, 1. That would have been 1 anyway with the plus. Doesn't matter. Okay, so either it's 22 or 22-ish. Okay, so this is going to be 4, 8, 9. Okay, so that says that the norm of this, at 0. Will be 3. So the unit tangent vector at 0, yes, only one at 0. I'm going to just divide each of these by 3. So it's 1/3 times 2 minus 2, 1. Okay. There. R double prime at 0. So let's do R double prime at 0. So plug in 0, you get 4. 4. That's 0. 2 minus 2 is 0. Okay. And lastly, let's multiply these together. So I want to take the dot product of R prime and R double prime. Okay. So if I do that, that's going to be 2t, 2 e to the 2t, times 4 e to the 2t, plus negative 2e to the minus 2t, 4e to the minus 2t, plus e to the 2t minus 2t e to the minus 2t times 2e to the 2t minus 2e to the minus 2t plus 4e to the minus 2t. Okay, so let's multiply that out. So this is equal to 8 e to the 4t minus a minus and plus is a minus 8 e to the minus 4t. And now let's multiply this all out. And so this will give you a plus 4e to the 4t. These will cancel, so it's a minus 2. Make that look a little nicer. And so that's a minus 2 plus 4. Why aren't those combined? Because there's a t there. Okay, so good. So that was a typo. There was a t. Okay, that makes a difference. Okay, so minus 2 plus 4t. Multiply, so you get plus a minus 4t. You get a plus 4 t e to the minus 4t. And lastly, you get a minus 8 t squared e to the minus 4t. Okay, so, oops, those don't cancel, but these combine. So the 8 for e to the 4t and the 4 e to the 4t is a 12 e to the 4t. And that's it. Okay, so minus 8e to the minus 4t. So those combined. Minus 2. The 4t's cancel. I can combine these last two terms. 4 minus 8 gives me a minus 4t e to the minus 4t. And that is your answer. Okay. Except for one stupid thing. T times t is t squared, which means those do not combine. And that is your answer. Okay. Problem number 40. Evaluate the integral. And so, the integral of t e to the 2t times I plus t over t minus 1 times j times 1 over rad 1 minus t squared times k. So first off, as good practice, let's try to look at the integral of, actually maybe give a little more space here. T e to the 2t. And let's look at it several ways. So one way could be using integration by parts. And so let's recall integration by parts. Integral of uv of u dv is uv minus the integral of v du. Let u equal t, dv equal e to the 2t dt. Then du equals dt, and v is equal to 1/2 e to the 2t. And so, let's do this. So the integral of t e to the 2t dt is 1/2 let's write t first, e to the 2t minus the integral of 1/2 e to the 2t dt. Well, I can integrate this last part. So this is just 1/2 t e to the 2t minus, well, the e to the 2t makes us have another half out in front. So it's 1/4 e to the 2t plus c. So that's one way of doing it. Let's use undetermined coefficients. To integrate this. And so I know that the integral of t e to the 2t dt will have some sort of basis involving t e to the 2t and e to the 2t. So let's take the derivative of both sides of this. So that gives me t e to the 2t is, well, the derivative of the first right over here, the derivative of the first, derivative of at times the second plus the first times the derivative of the second. Derivative of e to any exponent is just e to the exponent times, well, in this case, the derivative of 2t, which is 2, plus derivative of the second term. Well, that's just going to bring down my 2 out in front, so it's a 2b e to the 2t. And so, from here, I see that equating coefficients, that 2a must equal 1, and a plus 2b must equal 0. So a is equal to 1/2 from this first equation. And so 2b is negative 1/2, so b is negative 1/4. And so I get that the integral of t e to the 2t is just equal to 1/2 t e to the 2t minus 1/4 e to the 2t plus c. Okay, so that's how we do it with undetermined coefficients. Let me do variation parameters. So let me make one of the constants a variable. And so if I do that, note the following, that the derivative with respect to a of e to the at dt, if I integrate that, this is just equal to the integral of, well, we bring down the constant, which in this case is t, so this is just t e to the at dt. And so we just want to determine this when a is 2. And that'll give me my desired integral. Okay, so the derivative of a e to the at dt, well, I can take this derivative outside the integral, so long as everything is nice, which it is. And so this is just the derivative of the integral of e to the at dt. But I know what the integral of e to the at is. It's just 1 over a e to at. I can take the derivative of this using the quotient rule. So it's the derivative of the first, treating t as a constant. So I'm treating t here as the constant. And so this is just going to be t, e, derivative of the numerator, times the denominator, minus the numerator, times the derivative of the denominator, all divided by the denominator squared. So this is equal to 1 over a t e to the at minus 1 over a squared e to the at. And so let's evaluate this when a is equal to 2. Okay, come on, let me have my screen back. Waiting for my screen to come back. So when a is equal to 2, we have the following, that the integral, so you notice that it's this, the integral of t e to the 2t dt is equal to, well, a is 2, so it's 1/2 t e to the 2t minus 2 squared is 4. So it's 1/4 e to the 2t. Well, since we took the derivative, I'm always off by a constant. So plus c. Okay. So no matter what, this is what my integral is. Okay, now let's try to determine the integral of t over t minus 1 dt. Okay, so let's simplify this. So I can just use synthetic division. So this is 1, 0, 1 times 1 is 1 plus 1 is 1. So this says that t over t minus 1 is equal to 1 plus 1 over t minus 1. And so the integral is just the integral of 1 dt plus the integral of 1 over t minus 1. But the integral of 1 is just t. The integral of 1 over t minus 1 is ln of t minus 1. Let me have back control. Plus c. Next, let's determine the integral of 1 over rad 1 minus t squared. Okay. So let t equals, it doesn't matter if you let it be sine or cosine. For some reason I always like sine so that I don't have any negatives involved. So dt equals cosine theta d theta. And so radical 1 minus t squared is equal to radical 1 minus sine squared theta, which implies that 1 minus t squared is just equal to cosine theta. Okay, so, well, I'll assume that everything's nice so that I can have the correct sign on this. It's getting a little squeezed over there, so let's just sort of put it over here. Okay, so assume that theta is defined so that cosine is greater than 0. Okay, so now I have the integral of dt over rad 1 minus t squared. Well, this is equal to I said it was cosine theta d theta. And the 1 minus t squared was cosine theta. So they cancel. And so this is just the integral of theta, of d theta. And so I have that this is arc sine of t plus c. And so, lastly, I have the integral of t e to the 2t okay, come on. Give me back my screen. T over t minus 1 and 1 over rad 1 minus t squared, that this will equal one half t e to the 2t minus 1/4 e to the 2t t plus ln t minus 1 and arc sine of t plus some constant vector. And that is your answer. Okay. 53. Show that if r is a vector function such that the second derivative exists, then the derivative of the cross product of r with its derivative gives me the cross product of r with the second derivative of r. So let's do this. So the derivative of r cross r prime by Leibniz rule, or whatever we want to call it, I have r prime cross r prime plus r cross r double prime. Give me back control. Okay, this is getting, let me get some more room here. But I know that a vector across itself is going to give me the 0 vector. And so this is just equal to r cross r double prime. And that's what you wanted to show. Okay. Let me do problem number 57. If u, the vector function u, is equal to the vector function r dot r prime cross r double prime, show that u prime is r dot r prime cross r triple prime. Okay, so let's do this. So I have u. Let's take the derivative of this. So it'll be the derivative first, a Leibniz type of rule, times the second. plus the first times the derivative of the second. I'll probably denote it this way. Okay. Good. So this is equal to well, the cross product is of two vectors, A and B, is perpendicular to both vector A and vector B. Therefore, the cross product of r prime with another vector is perpendicular to r prime. And so its dot product is 0. So I know that this is 0. Okay. And so let's take the derivative. So I have r dot, and now let's use the Leibniz rule again. So it's r double prime cross r, so derivative the first times the second plus the first times the derivative of the second. So that'll give me a triple product, a triple derivative. Okay, so again, a vector cross itself is the 0 vector. So this is just equal to r dot r prime cross r triple prime. And that is what you wanted to show. And so we are done for today. That's all